This is a high school Algebra 1 lesson on how to graph absolute value equations. You would already need to know how to solve them. Check with other videos, but here's how we graph them. Okay, each one of the types of equations that we'll study in Algebra 1 has a distinctive shape. And the distinctive shape of absolute value is a V. This is the graph of the simplest one, the function f of x equals the absolute value of x. No adds, no subtracts, no multiplies, divides, just plain vanilla. Some characteristics of it. There's a point at the bottom. It opens to the top, kind of like. Big at the top, small at the bottom. It's composed of two straight sections. They're rays that meet at a right angle at the origin. We will use this to compare to all of the others. Let's see how we got it. You can see here if we have put in -2 in the absolute value, we get 2. Absolute value of -1 is 1, and so on. When we go to graph it, this would be the point 2, 2, 2, 1, 1, 1, -1, 1, -2, 2. Okay. This is a characteristic shape. We'll compare the others to it because all others are related to it, in a sense come from it. We call it the parent function. And the parent function is a big V with a right angle, looks just like that, opening up, point at the bottom. Okay, let's discover what a few of them look like by playing with them. Okay. In your cipher, write this down so that you'll learn it good. And let's see how this works. Okay, this one is like super simple. We're going to compare it to the parent function. So I've written it this way. First off, make ourselves a t-chart. And then the t-chart, go ahead and make it like this. This will be, this is g of x, which is the next one after f of x. We're talking about this one. We're going to compare it. So in the same exercise, we're using f of x. We can't call this one f of x. We could call them both y if we wanted to. But so as to distinguish them, remember f basically is because it's function, and that's the first letter. And then the next one we usually use is g because that's the letter that comes after f. No real creativity in naming, but it works. So g of x is the same as y. We'll have x and g of x. Yes, do write this down. G of x, to reminder, is y. Then we're going to just choose some points. And we'll do, I'm just going to do 2, 1, 0, -1, -2. Put in 2 for x. Absolute value of 2 is 2, plus 5 is 7. Put in 1 for x. Absolute value of 1 is 1, plus 5 is 6. Put in 0 for x. Absolute value of 0 is 0, since it's not at all distant from 0. That plus 5 is 5. Absolute value of -1 is +1, plus 5 is 6. Absolute value of -2 is +2, plus 5 is 7. So we'll come out here and we'll graph them all out. We come on up, and now we'll go up to 1, 5. I'll start with 0. 0, 5 will be right there. 1, 6 will be about here. 2, 7 will be about right here. Not going to use a 3. -1, 6, about right here. -2, 7, about right here. We're going to get the characteristic V shape. Okay. Difference is it is slid or shifted 5 units up. So it's the same shape. It's still a right angle, but the vertex, the whole thing, just slid up or shifted up 5 units. Here's one that looks a little bit prettier. Okay. So Here's the characteristic parent function f of x. Here is g of x equals the absolute value of x plus 5. We notice some observations here. The plus 5 is outside of the absolute value symbols. And the result of adding in this fashion was that the whole graph shifted up 5 units. Okay, so let's try the next variation. Again, write these down, copy it, make the little picture, draw the little f of x as the parent function, draw the whole thing, okay? Because you need to know what you're doing. Okay, so again, we'll do it again. X and g of x, which of course is y. Now we're going to do absolute value of x minus 4. Okay, I'm going to do the same things here. I'll do 2, 1, 0, negative 1, and negative 2. You can do these in any order. I just happen to be doing this. Okay, so if I put in 2, I'll have 2 minus 4 is negative 2. Plug in 1, substitute 1 in for x. Absolute value of 1 is 1, minus 4 is negative 3. Substitute in 0, that'll be negative 4. Substitute in negative 1. The absolute value of negative 1 is positive 1. Minus 4 is negative 3 again. Substitute in negative 2. Absolute value of negative 2 is positive 2. Minus 4 is negative 2. So what's going to happen this time? Okay, well, 0 is going to go to negative 4. We'll say that's about right there. Okay. Negative 1 to negative 3. Negative 2 to negative 2. Then 1 and 2 will come up right like this. And we'll get a v that is lower. Again, the minus 4 is outside of the absolute value signs. It's not part of the absolute value expression. The whole absolute value graph moves down 4. It's minus 4. It moves down 4. To look a little bit prettier, this is what it looks like. Grab it. There we go. Okay. So what do we have here then? We have that relative to the parent function, f of x equals absolute value of x, subtracting 4 from the expression lowers the whole graph. It shifts down 4 units. Okay, both of these, the one we just did that was up and down, a reminder it was outside of the absolute value signs. Let's try one that's inside the absolute value symbols. Okay, well, we're going to do g of x is equal to x plus 3. Okay, let's do that again. Same deal, copy it down, work it out. But in this case, let's start with 1 and go down like this to about negative 5, I guess. So now it's inside. It's the absolute value of x plus 3. 3 plus 3 is part of the actual absolute value expression. So we'll do 1 plus 3 is 4. Absolute value of 4 is 4. 0 plus 3, 3. Absolute value is 3. Negative 1 plus 3 is 2. Absolute value is 2. Negative 2 plus 3 is 1. Absolute value is 1. Negative 3 plus 3 is 0. Of course, that's not distant from 0. Then negative 4 plus 3 is going to be negative 1, and the absolute value of negative 1 is positive 1. Substitute negative 5 in for x. Negative 5 plus 3 is negative 2. Absolute value of negative 2 is positive 2. Okay, let's see what this looks like. 1, 4. Okay. 0, 3. Negative 1. I'm going down. Negative 1. Okay, I got to 0. 0, 3, negative 1, 2, -2, 1, -3, 0, -4, 1, and now it's going back up, and there's our V. Okay. Now notice, curiously, you might have expected that it would shift by a positive number, but this is one of those anomalies that we'll learn more about later why, but it's not negative. It's not when it's inside the absolute value sign, it's the other one. So instead of shifting to the right, it shifts to the left. Here's it a little prettier looking. Okay. So this is the vertex of the V, of the angle, shifts 3 units left. Again, this was +3 inside the absolute value sign, and it went so that the vertex is at -3. It shifted to the left. You might have expected to the right, but it's to the left. Okay, now, I'm not going to do it, but if this were -3, it would shift to the positive, to +3. Okay, I'm not going to do that one, but it works both ways. If it were x -3 in the absolute value, then the red one, the shifted one, would be over here. Okay, let's try this one. Okay, we're going to multiply outside the absolute value sign. See what happens. Make yourself a chart. X and g of x, which of course is y. This time I happen to know it'll work okay just to do 2, 1, 0, -1, -2. Absolute value of 2 is 2 times 2 is 4. Absolute value of 1 is 1 times 2 is 2, and on down. So what's this one going to look like? Okay, we've got 0, and we've got 1, 2, and -1, -2. At 2, the value is 4, someplace up here. At 1, the value is 2, along in here. -1, it's 2. -2, it's 4. So it's going to look something like this. It's narrower, it's squinched up. So a prettier drawing here. Here we go, drawn a little bit nicer. We would say that the V is narrower, or that we would say that it is stretched vertically. So here's Froggy to help us remember what stretched looks like. So you have Froggy, and if you pull on Froggy and stretch him, he stretches out, and he gets skinnier. He gets narrower. Okay, so stretched vertically is what's happening here. The V is narrower. Notice that the number that was multiplied on the outside of the absolute value expression was bigger than 1. Here I'm talking absolute value. Okay, bigger than 1. So we'll see what would happen if it were negative. But this one is positive, and it's bigger than 1. In this case, I'd be talking as -2 in the same deal, making it making it narrower or more stretched. Okay. Let's see what happens to this one. Draw it out. Why don't y'all draw this one out? Do an x and a g of x. Take a moment and pause it. Make sure you draw your reference parent function. Go ahead and graph it and see what happens. So pause it for a moment. Okay, this is what you should have gotten. The V is now wider or shrunk vertically. So again, we'll let Dr. Dog help us with this one. So here's Dr. Dog. He gets shrunk and he goes out fatter or wider. Okay, that's what happens when you get shrunk vertically. It widens out, it opens up. Notice that all of these have opened to the top. We didn't change that. We shifted it left and right, up and down, but in each case it's had the little point at the bottom and the big at the top. Okay, when When we multiplied on the outside by one that was bigger than 1, it got narrower. It stretched from being big. And when we multiplied by a number that was smaller than 1, but still, you know, the absolute value, smaller than 1, then it got wider, okay? Or shrunk vertically. All right, here, y'all try this one. Go ahead and draw you out a t-chart. That'll be x and g of x, which is the same as y. Go ahead and do this one. -3 on the outside. -3 times the absolute value of x. See what that looks like. Pause it now and do it. Okay, here's what you should have gotten. Notice what happens. It's now upside down. Okay, this particular one, it now opens down instead of up. That's because of the negative. You see the effect that it has? It negates everything. Okay? And now then it opens down, and it is, this one was a 3 on the outside, which absolute value bigger than 1, so it got stretched. It got stretched or narrower. Okay? So hopefully this will be helpful for you in doing them. And here endeth the lesson.